Imagine a phenomenon that appears for 2 seconds, once every few years, during the worst possible conditions. No second take, no controlled rerun. If your camera points the wrong way, it's gone. Tonight we're not chasing conspiracy. We're chasing measurement pain. 5 real events that stay mysterious because they're rare, unpredictable, and easy to confuse with noise. People think science avoids certain topics. More often, science is stuck with a brutal problem, not enough clean data. If you get one messy signal, it's irresponsible to declare a grand theory. This is why rare events feel forbidden. It's not fear, it's standards. Scientists would rather say, uncertain, than sell a story they can't verify. Repeatability turns weird into reliable. Rare events block that. If you have only a handful of sightings, every explanation competes with errors, misperception, bad timing, flawed sensors. Without repetition, you can't build strong statistics. So rare event science becomes detective work, collecting fragments and refusing to overclaim. We record what stands out: bright flashes, loud bursts, dramatic clips. Quiet cases vanish. That skews the dataset toward extremes. Patterns get distorted, and the true distribution stays hidden. In rare events, what you don't record can mislead you more than what you do record. That's why good researchers obsess over boring details like thresholds and coverage. In this domain, the instrument is never innocent. A weird signal can be the universe, or your equipment. Sensors can saturate, antennas can pick up local interference, algorithms can produce artifacts. Before you explain a rare event, you must prove it isn't a false positive. That's slow, unsexy work, yet it's the only way real anomalies survive. A thunderstorm, a sudden flash, and then, witnesses report a glowing sphere drifting slowly, sometimes near the ground, sometimes near a window. It's described as stable for a moment, then gone. The weird part is behavior. It doesn't act like a normal lightning bolt. But the bigger problem is timing. Most people see it when they're panicking and unprepared to document. Storms are chaotic laboratories: rain, wind, electromagnetic noise, low visibility, fear. Cameras struggle, compression ruins detail, and distance is hard to judge. Even if ball lightning is real, its trigger might be a rare combination of local conditions, meaning you can't reliably recreate it. You're trying to measure a fragile recipe while the environment actively destroys your instruments. There are proposed mechanisms, plasma-related processes, vaporized material, electrical field interactions near strikes, but a single, repeatable model still isn't locked. The careful view is layered. Some cases may be misidentifications, but a smaller set of high-quality observations suggests a real, rare atmospheric electrical phenomenon. The mystery survives because the event refuses clean replication, not because science refuses to look. Radio observatories detected bursts that looked suspiciously astronomical, rare, sharp, and confusing. For a while, they lived in the same mental category as deep space mysteries. Then the twist landed. Many Perytons were traced to an extremely local action, opening a microwave oven door mid-cycle. A cosmic-looking burst, created by a human routine mistake. Sensitive instruments amplify everything, including your own environment. Local electronics can impersonate the sky if they leak in the right way. Perytons prove why. Boring suspects come first: hardware quirks, timing errors, and human behavior. It's not embarrassing, it's essential. The universe is not the only transmitter. If you don't eliminate local interference, you'll build myths out of your own kitchen. Solving Perytons didn't kill wonder. It cleaned the dataset. It removed a false positive population so genuine anomalies stand out more clearly. That's how science advances. It doesn't just explain, it filters. And filtering is what makes the remaining rare signals more trustworthy. In the rare events world, debunking is not cynicism, it's quality control. Some spacecraft Earth flybys showed small, unexpected differences in tracked speed. Not dramatic, no sci-fi leap, just tiny residuals that shouldn't be there in a perfect model. But navigation is a precision game. When you're counting millimeters per second, even small unexplained leftovers matter. They can reveal missing corrections, unmodeled forces, or subtle issues in tracking and time standards. A flyby mixes many moving parts: Earth's gravity field variations, rotation, station geometry, timing, atmospheric effects at the edge, and relativity corrections. If any piece is slightly wrong, the leftover looks like a ghost acceleration. You're hunting a needle in a hurricane of math. Rare event science here is accounting, proving whether the anomaly is physics or bookkeeping. The responsible stance is cautious. Compare missions, recheck data pipelines, refine models. Some analyses suggest the anomaly may shrink as modeling improves. Others keep it on the table as unresolved in specific contexts. That uncertainty is not fear, it's discipline. Precision science moves slowly because a single false, new physics announcement can damage trust for years. Fast radio bursts are milliseconds-long flashes that arrive from far beyond our solar system. They're real, seen by multiple observatories, and they're powerful enough to cut through space like a shout. But they're hard to study because they're brief and unpredictable. If your telescope isn't watching the right patch of sky at the right moment, the burst is simply lost. Some FRB sources repeat, which is a gift. Repetition allows localization and deeper study. But repeats aren't scheduled, they're irregular. Days, weeks, months, sometimes silence. That means you still can't run controlled tests. Theories range from magnetar activity to complex environments shaping the signal. The larger point is methodological. Even when a signal is real, interpreting it requires careful statistics, not one dramatic detection. With distant sources, you can't inspect the engine. You only get a signal shaped by interstellar plasma, instrument sensitivity, and detection algorithms. A burst is a clue, not a full story. As more detections accumulate, patterns emerge: distributions, repeat behaviors, host environments. FRBs show the modern scientific path: inference under uncertainty, improved by better arrays and cross-validation, not by a single perfect moment. Above thunderstorms, the upper atmosphere can flash in strange ways: sprites and elves, brief luminous events high above the cloudtops. Early reports sounded like folklore, pilots seeing red glows and rings. The reality is timing and geometry. These events are fast and often faint, and most cameras historically pointed down at the storm, not up at the air above it. Skepticism was rational because early evidence was anecdotal and hard to confirm. Sprites can be milliseconds to tens of milliseconds, elves can be even faster. If your sensor is slow, it misses them. If your lens is narrow, it misses them. Once low-light cameras and high-speed sensors improved, these phenomena became measurable and repeat observable. The taboo was never cultural, it was technical blindness. Sprites and elves demonstrate a simple truth: nature can run entire categories of events outside our sampling. If you don't measure it, your model is incomplete. Many mysteries are actually maps of instrument coverage gaps. Expand coverage, and the universe doesn't become less strange, it becomes more documented. That's the most honest kind of progress. These 5 cases live at the edge: too rare, too fast, too distant, too noisy, or too dependent on chaotic conditions. That's why they attract myths. But the real drama is methodological: separating signal from error when you only get one shot. Rare event science is the art of refusing easy conclusions while building better ways to capture reality next time. It's not secrecy, it's infrastructure: better sensors, wider coverage, time synchronization, redundancy, and careful pipelines that can detect and reject false positives. Over time, some mysteries collapse into mundane causes, others become new fields, and some remain unresolved because nature won't cooperate. This is not fear, it's a commitment to truth even when truth is incomplete. If you want the real edge of science, follow the hardest measurements, not the loudest claims. Which case felt most unfair to study: storms, spacecraft tracking, or deep space bursts? Comment your pick, and if you want a deep dive, I can make a full episode on one case with competing explanations and what evidence would actually settle it.